All right, another distribution that we haven't talked about yet that comes up as that we can express as a transformation of another family of distributions we know is called the Cauchy distribution. Okay, so here's how we come across the Cauchy distribution is that we suppose we have a laser pointer. So the laser pointer is 1 unit of length away from a wall. So we have kind of an infinite length wall. And there's a laser pointer, let's say right here. Okay. Say that the laser is 1 unit away from the wall. So it's mounted on a rotating disc. So it's rotating kind of 90 degrees in either direction, 180 degrees of movement. The center of the disc is 1 unit away from the wall. And the wall has infinite length. So the disc spins repeatedly. Between, we'll say, minus 90 degrees and 90 degrees. So the disc is spinning between in this way, right? So, and what happens is at some point it's going to stop. Okay. So it's spinning on a disc, so it's a circle, but it only turns on, sorry, it spins repeatedly and only turns on when it's facing the wall. And so the question is, what is the distribution of marked spots on the wall? So, geez. So it's spinning, and as it's facing the wall, it's marking the wall. But what you'd expect is that it's going to mark the wall more concentrated around the perpendicular, because as it spins through there, it's hitting every point. And as it goes off to the edge, it's still hitting the wall, but it's going to be more sporadic. It's going to be more not as concentrated, right? Because of the angular issue. So how do we model this? This is a little bit of a complicated one. So we're going to let X be the angle of the laser pointer with respect to the perpendicular line. Okay, so this is X. And we're going to note that that angle, okay, is uniform. Right? So, and Y is going to be the point on the wall. So, and Y is the point on the wall. So in this case, we can actually express Y as the tangent of X. X is an angle. And we're assuming that X is uniform minus pi over 2 to pi over 2. So X is essentially going at a unit at a constant speed. Okay. So Y actually is smooth and increasing. Right? The tangent function between minus pi and pi, minus pi over 2 and pi over 2 looks something like this, right? Minus pi over 2 to pi over 2 looks something like this, right? So this is tangent. And we see it goes off to infinity. So if you're at pi over 2, you're pointing pretty much straight out. But the wall's of infinite length, so theoretically you're hitting a point way out. Okay. So the change of variables formula does apply. The distribution of X is uniform, right? The transformation is tangent. The inverse of the transformation is the arctangent, right? The inverse tangent. And the derivative of the arctangent is 1 over 1 plus y squared. So we can use this to get the density of y. What's the density of y? Density of y is density of x evaluated at h of y, absolute value of the derivative of h of y. Well, y has to go from tangent of negative pi over 2 to tangent of pi over 2, right? So actually y is minus infinity to infinity, provided that we only allow okay, it's minus infinity to infinity. And the density of x is 1 over pi. And the derivative of h is 1 plus y squared. So y is called standard Cauchy. Now, what's interesting about this is that the Cauchy distribution can be misleading because if we plot the density, this is what the density looks like. So it looks kind of like a bell shape, but a bell shape does not always, not all bell shapes are created equal. So remember the bell shape of the normal, standard normal, had 99.8% of the mass between -3 and 3. That's not true for a Cauchy. We know that the way this was generated, if we're pointing out at an angle very close to pi over 2, we're going to be way out in the wall. We're not going to be between -3 and 3. And it's not that unlikely that we have an angle like that, right? So in particular, what's the probability that y, the Cauchy, is bigger than or equal to x? Well, of course, it's the integral of the density from x to infinity. Now, 1 over 1 plus y squared, if we have a very large value of x, so imagine we have a very large value of x, that's kind of like 1 over y squared, because the 1 doesn't really contribute. So this is 1 over pi x y squared, which we can easily integrate. This is 1 over pi x for large values of x. So meaning that for the Cauchy to be bigger than or equal to 1,000,000 is about 1 over 1,000,000. 1 in 1,000,000, which is small, but if you did it for if you calculated the same probability for a standard normal, you'd see that it's infinitesimally small, something like 10 to the minus 60 potentially, something extremely small. I'm not saying that's exactly what it would be, but it would be it would be orders and orders of magnitude higher. And furthermore, because of these heavy tails, the expectation of the Cauchy does not exist. So this is an example of a random variable that does not have an expectation. And the reason is because if we take the expectation of the positive value of y, so this is the integral 0 to infinity of y times the density, we can do a u substitution, right? The u substitution is 1 plus y squared. Du is 2y 2y dy. The limits of integration now go from 1 to infinity. It's du over 2 pi of u, which we know from calculus the integral of 1 over u is infinity. And similarly, same calculation would say that the expectation of y minus, which is the negative part, is equal to infinity. So both positive and negative parts are equal to infinity, and infinity minus infinity is not defined, so we do not have an expectation. Okay, so here we've now gone through several examples of monotone transformations. We've seen the gamma distribution, we've seen the exponential arise in this way, the Rayleigh distribution, now the Cauchy distribution. We have the change of variables formula, which allows us to easily compute densities of monotone transformations. But not all transformations are going to be monotone, and so we're going to see how we can build upon this change of variables formula for monotone transformations. Next time, we're going to talk about how we can do many-to-one transformations.